for today is Dr. Robert Knight. He's a professor of psychology and neuroscience at UC Berkeley and a professor of neurology and neurosurgery at UCSF. He also serves as the Director Emeritus of the Helen Wills Neuroscience Institute here at Berkeley, the Chief Editor of the Science Journal for Frontiers for Young Minds, and the Chief Science Advisor at NeuroFocus Incorporated. Dr. Knight's lab uses a variety of methods, including electrocorticography, electroencephalography, and behavioral analysis to study how areas of the brain, in particular the prefrontal cortex, are involved in human behavior. For his outstanding research in neurology, Dr. Knight was awarded the Jacob Javits Neuroscience Investigator Award from the National Institute of Neurological Diseases and Stroke. Widely considered an expert in neurology, neurophysiology, and cognitive processing, Dr. Knight continues to make groundbreaking contributions to cognitive neuroscience. Please welcome Dr. Knight.
Thank you. So first, thank you, Bridget, and thank you for all the organizers of this. It's really amazing to see all these talents in the room, and this really beautiful Saturday afternoon. Before I get started, I'd like to just thank three of the people in my lab who have posters here today. I don't know where you are. Jennifer, where are you? Somewhere. Okay. Jenny, where is Isabel? Where are you? I lost her. Someone's here. There she is. And Cal. Where's Cal? Thank you. And thanks to the other cots I made who work in my lab. That's been really incredibly valuable. Who did this in my computer? What is this? What did you do? I don't want to use words. What happened? What did you do? How did this get? Thank you. So first a couple things. Bridget said this was going to be on communication, so I thought that I'd really narrow this talk down to some of our work on physiological underpinnings of language, but I thought since it's communication, I'd introduce a form of communication first to let you know where I am from. So, you all know that's Jaws, and that's where I'm from. Jaws happened in 1916, and it was a crazy shark that went up the coast of New Jersey, killed one person there, another person there, shut down the east coast in panic, went up into the Raritan Bay and up into this little teeny creek, Madeline Creek, where it killed the last two kids who were swimming. And then it basically floated around in the bay for a while and then came back. And about 3 days later in Lawrence Harbor, which is where I grew up, it was caught by two kids off this beach dragnet. So that's actually the story of Jaws. That's my brother. So, is there anybody here from New Jersey? 1, 2, 3. Excellent. George, you don't count. Really, if you're from Jersey, you really shouldn't ask someone from Jersey to give a speech on language. You don't believe in the Queen's English. So there's a little problem. So let me show you why I don't think I should be giving this talk. I put together what I consider the top 5 reasons I shouldn't be giving this talk. Now, this is my wife, Donatella. She's actually Italian, so she has English as a second language. This is my colleague, Nina Drock, who's an expert neurolinguist, and they both have the audacity to continually point out when I'm speaking incorrectly. It's not aphasia, it's just... So number 5, these are things they say, they tell me I said. Okay, very less possible. Seems normal to me. I'm doing good, everybody. If I'm saying I'm doing well, I feel weird in my brain. It's like creepy. To who? That seems right, but it turns out, I'm pretty sure it's to whom. They inform me. I should have went to the meeting. That's another one. If I try to say I should have gone to the meeting, I get an N400. Semantic mismatch. And then finally, most importantly, how you doing? I'm Thursday. Okay. Am I done? Am I doing enough? Come on, good. All right. So let's get a little more serious here. And by the way, I really enjoyed the fire talk. Gary. That was the, I think you're going to see some of this theoretical work. It maps onto patients and it maps onto this whole notion of language. So we can go back to 1968. Norman Geschwin first was it just a study of looking at post-mortem brain showed that in humans with that there's a hemispheric biological anatomical asymmetry with the left posterior temporal plane widely connected to language decoding areas was larger. I mean, just physically larger on the left than the right. It was really a very simple but powerful observation. We can go back much farther back in time, and as you heard before, this notion of this Perisylvian language region that allows you to decode the meaning of input, either visually in reading or auditorily in speech, so-called Wernicke's aphasia, and then this output area that somehow, basically is critical for speech output, somehow selects what's going to be put forward. And this is really kind of the standard notion, Broca and Wernicke's. And what I'm going to try to lay out to you is some physiology that supports this, just like you saw some of the patient research that supported the semantic and phonological layered model that Gary presented. So let's start by just showing you a couple patients, and probably some of you in my 117 class have seen this. It's pretty standard Broca's aphasia. The man understands what I'm saying. Just watch about 30 seconds of the interaction.
Let's check your language out now. Can you tell me what happened when you had the stroke?
Yeah, sitting there, yeah, sorry. Oh.
Do you remember, was it in the morning or the afternoon?
TV, no, TV.
11?
Yeah.
11 in the morning?
Yeah.
11 in the morning. Okay, so he's understanding what I'm asking him, but he has a non-fluent output of speech, sometimes just single utterances, but he's trying to communicate the correct content. He knows the question. He's showing me it's 11 a.m. Can you tell me, where were you born?
63, 68.
63, 66.
60.
I see, okay. Where were you born? What city?
Windwood.
Where?
Linwood.
Linwood?
No, Windwood.
Let's just try some simple language things. What's this called?
To be.
A what?
To be is to be.
A tubie. It's kind of a phonemic error for toothbrush. He certainly knows what it is.
So here's another patient, even a shorter little one, and this gentleman knows what he's supposed to do, but he can only put out one or two words with the answer to how he's supposed to describe these objects.
Completely as possible, tell me what you do with each one of these.
Matches.
Tell me what you do with that.
Start fires.
Start fires. So he knows what it is,
Pen.
but he can only put out a truncated couple word sentence. This classic, the meaning's there, but it's telegraphed. The opposite kind of patient with a posterior lesion, this man actually had a hemorrhage in his left hand.
First, I'll ask Mr. Corman, how are you feeling today, sir?
Pretty good, yeah, actually. I just not a pencil where I'm going, But I'm passing there, and then I got things moving on vegetables, vegetables, but I'm really not actually not really enhancing out there, I think.
Are you having any headache
from the migraine?
Did your head hurt you at all?
Speech doesn't make sense.
Yeah, I guess we are, it's not on my Asperger's sense, but it's whatever, that's his Dan, but it's not true.
And interesting, he talks to me as if I understand him. Right? He's not quite totally into the fact that what he's saying is pretty much linguistic gibberish. Everything from the lexicon up to the sentence structure, up into higher level parts of language have fallen apart. Here's a gentleman again, he's shown a picture of a picnic scene, and he's just being asked to describe it. That's all. And you're going to see again, his speech is fluent but empty. And he again, like the other gentleman, if you asked him to do things and follow commands, would have a lot of problems. Whereas the Broca's patients I didn't show you, because their comprehension is intact, they can do tasks.
Well, this is a picture that has been in the test of some sort, someplace, where you guys all within doing over there. And I always started on this side, starting and going this direction. But I was interested with the man who was a doctor guy who was sitting around with the foods and asking, and he's writing books,
Comprehension problems.
and he
Lots
was
of words.
interested in the activity.
Non-psychotic speech, right? This is a language disorder. The psychotic speech, individual sentence structures intact. How they parse them and put them together is tangential, crazy, but the actual structure is intact. What other neurological evidence do you know about language organization? I think one of the most elegant examples was the work done in the 60s by Michael Gazzaniga, who is now at UC Santa Barbara. Here's your big corpus callosum. It connects your two hemispheres. It's a big, rapid information transfer bundle. And in certain patients with severe uncontrolled epilepsy, and I'm not going to go into the details of the epilepsy, certain patients can benefit from actually surgically cutting the corpus callosum. Surgeon literally goes in and cuts the one side from the other side off to kind of decrease the spread of seizure activity and get the patient in better control. And this is actually what it would look like post-operatively. It's quite restricted. This is a cut like this, a coronal cut. The corpus callosum is literally transected. Gazzaniga studied these patients, and I think you'll see here the classic effect that he reported at the start. First, they presented things quickly, the cystoscopic methods to the left or the right field. And what they found basically is that if they presented let's say, the word key ring to the person, with the person fixating here, the person would only be able to say they saw a ring. He would not get into their conscious access because it was trapped in the non-dominant, non-linguistic right hemisphere and could not. What you normally do is you see this here in the left hemisphere, you see this here, you transfer the visual information over in 10 milliseconds. You don't even know what happens. Boom, and you just put it together. But this patient, his language is trapped. So what does it look like clinically? And Mike gave me one of his original movies, and you're going to see this patient, when the patient is being asked to do things, the patient has a complete section of the corpus callosum. So they're being asked to do things, and they're being asked to do things with the right-handed verbal command, which is very easy because their left hemisphere, this person is language dominant. They can hear the examiner saying, do this, decode it, and implement it, and make a movement. And then with the eyes open, if Mike says to this patient, well, do the same thing with your left hand. The patient fiddles around and then gets the hand in the same position. But they're doing it really on a visual match. They're not doing it on language. Because as soon as Mike tells the patient to close their eyes, the patient can do everything to verbal command with their right hand. And now the left hand has no idea what's going on. Because the information cannot basically get into control. So take a look here. This is a really very telling patient.
With your left hand, make a fist. With your right hand, make a hitchhiker's gesture. Good. With your left hand, make a hitchhiker gesture. Good. With your right hand, make a, with your left hand, make the motion of like using a screwdriver.
With which hand?
A screwdriver with the left hand.
With the left hand.
With the right hand not doing it, and nothing to mirror, they can't do it. Old motion comes back, thumb comes back.
All right, try it with your right hand. Okay, now with your left hand. Okay. Now, okay, with your right hand, make the A-OK sign. How about with your left hand? Okay. Now let's close your eyes.
This is the key.
Your eyes closed? All right, with your right hand, make me a hitchhiker sign. With your left hand, make me the A-OK sign. Eyes closed.
Eyes are closed.
Can't do it.
Okay, now with your right hand, make a screwdriver.
Control the left hand. The classic.
With your left hand, make a screwdriver motion.
Old science came up. What's wrong? Kind of like the characteristics of the movement.
Okay, that's very good.
Okay, did everybody see that? Because that's the classic split brain. The patient cannot use their left, they cannot control their left hand to verbal command because basically language is trapped in the left hemisphere. It can't go over to get this hemisphere to make the left side of the body work. So this finding, and of course the long history of aphasia, clearly pointed out this idea of hemispheric lateralization, gave us some ideas of localization, etc. So I'm going to show you some data, and I just started the people who, I'm going to show you data from Christian Makuta, Eric Edwards, Brian Knopke, Dean Clinker, and Brian Paisley. We'll mention them again as we kind of move along. So we have to go back really to preface the physiology part of this talk. Really in 1928, 29, Hans Berger discovered the EEG. He also did, he was one of the probably first people ever to do direct cortical recording electrocorticography. And the rest of this talk is going to be focused on electrocorticography. And let me show you what I mean by that. In essence, it means recording electrical signals not from the scalp, but directly from the patient's brain. What's the principal method for analyzing these signals? And I'm not going to go into this in any depth other than this particular group knows what spectral analysis or Fourier analysis is. You can take any signal and you can break it into its constituent subsignals that put together with you that signal. If you're, I like to say the class, if you're listening to a jazz club trio, you can break it down into a lot of bass and a lot of piano and so on in terms of power. So we use this time frequency decomposition of signals to get some insight into how your brain is doing things. And again, I'm going to focus on language, although as Bridget said, my main interest in the lab is actually executive control. But Bridget told me what to do, so I'm going to do it. She like that all the time. No? Yes? What? Where are they? Where are they? Is she like that all the time? Yeah. No, I didn't say anything. It's ridiculous. we need to talk afterwards. Sorry. Yeah. Okay, so anyway, just quickly again, what I want to, I know a lot of you are not really into neurophysiology, but I just want to point out to you, as you sit here in this room, as you're doing perception, as you're seeing things, as you're generating thought, as you're moving your body limbs, the principal brain signal in your cortex that's tracking all this is what's called high gamma. It's a high frequency oscillation between 60 to maybe 250 hertz. It wasn't even discovered in the human cortex until 1998, but it turns out to be the most powerful signal tracking cognition. It also is the driving force for the fMRI full response. So how do we get involved with this? The surgeons at UCSF asked us to help them develop an intraoperative mapping procedure so they could quickly figure out in the operating room what the person's language was so they could tailor their surgery and miss language as they were going for some kind of brain lesion. So you're going to see this is a patient, she's about to have her language map in the operating room. And she has to be awake when we couldn't map the language.
Okay,
That's the cardiovascular pulsation. This is wide awake.
You feel some vibrations, Susan.
Dr. Berger, chief of Neurosurgery, is fabulous.
Get ready to do the mapping.
So once we've kind of mapped out her languages and stimulation, we then have a 10 minutes where we put up high density grids right on the pain temporal areas, which you heard earlier in regards to learning area, speech comprehension. Okay, so the grid's on there, and we can do these very short but very focused experiments. So we decided to start just to calibrate ourselves to make sure we're not out in fantasy land, to see if we could record in the operating room. It's not It's a tough environment electrically. There's lots of things ripping, clicking, and making, there's a lot of artifacts, so it's not easy. We want to be sure we were getting those signals. So we first focused on a real simple signal called the mismatch negativity. This is as simple as you can get. Basically, when you get a little deviation in a stream of sensory input, you get a little orienting response. And we knew from many other studies that I'm not going to go into that the source was right in the temporal plane, this orienting signal. So we reasoned if we couldn't record this, we were basically, really on a fool's errand. So it turns out we could, and I won't show you the actual event-related potential activity, the mismatch negativity. I'll show you the time frequency, and this is where we got onto the fact that there was high frequency response in the cortex. Beep, 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 we get a response at 100 milliseconds with power up to 40 hertz. Beep, 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 deviant. We dishabituate the early response, it gets bigger, more power, but in addition, we see this cloud of high frequency response between 70 and 160 hertz. And this is really, to our knowledge at that point, had never been described in the human cortex, so we thought it was an artifact. Of course, we did lots of studies, and we repeated it with phoneme mismatches, ooh, 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 ah, and we found this high frequency activity. It turns out that it's incredibly robust, and now there's probably between 50 and maybe even more labs internationally who have access to intraoperative recording to actually try to understand brain phenomena using this response. This is the guy who led the study, Director Emeritus. He was a psychology PhD here at Berkeley. Now, a dean followed up and produced some information that I think is extremely important as you think about how the brain is organized, because I want you to forget about the idea of blobology. There's 3 centimeters of this that does that. This does this, and it gets a little dangerous if you just look at PET or fMRI. This is directly on the surface of the brain. There's a high-density grid right on auditory, Wernicke's area here. And here's basically 9 electrodes. And each electrode is only 4 millimeters from the other electrode. The study's really simple. You need to keep it simple in the operating room. The patient either hears a word or they speak a word. Well, here's these 9 electrodes, and this is the power in the frequency in the cortical response going at 200 hertz. You can see that electrode, that one, that one, that one, that one, that one, that one, that one. There's a huge response in this high frequency band when you hear the word. But the electrode right in the middle actually shuts off and only comes on when you speak. So this idea of this simple serial model and everything happens here and everything happens here, I don't think it's true. I think there's all things are very interleaved and very parallel, very quick. And it's a much more complicated cortical microstructure than we actually believe at the moment, which is good. It gives you more information to kind of model and understand cognition. And you can even see it at the single sweep level. There's this high frequency response. One triad, you can see it here. And in the nearby electrode, nothing. And then when the person speaks to one trial, we get a response. So it's really a beautiful signal for monitoring the brain. It also has very, very rich information in the higher level linguistic space of phonemes and even words. So this is a grid from a patient, and this is a grid where we see black. It just means the signal was there, the electrodes for contact. And these are matched in length, let's say, ba, 700 milliseconds, or a word. And you can see this incredibly rich distribution of different powers and different activations just in this little area. Now this is really nice because, as you'll see at the end of the talk, it means there's a tremendous amount of information in these grids. And I'll show you what we're trying to use is to extract that information to develop a speech prosthesis. So we actually decode from direct recording this activity and turn the electrical activity into a word so that a patient with a debilitating problem like Lou Gehrig's disease, ALS, thanks to Stephen Hawking, or Broca's aphasia, who knows what they want to say but can't speak, could we get a speech prosthesis? So let's hold that to the last part of the talk. I just think it's really incredibly rich. And even though the sound's on this whole time for the phoneme, really all the information's there before you get into the ah part, and the brain just stops responding, where a word, like finger or whatever, has this very extended and very rich distribution of activity. And I should just say, we think the optimal spacing for independent information is 1.5 to 2 millimeters, we think, and we're working on higher density grids. Okay, so how can you use this to do something? Well, it's one thing to drive the cortex. Can we use it to address, kind of classic psychological and acoustic theories? And I think one of the first ones we went after was categorical perception, and that's just this wonderful property that we tend to chunk things. It's all ba ba ba, and then it's all da da da, and then it's all da da da, or it's all dog, and then it turns to all cat. So the question was, in categorical perception, did you take everything? Was there some kind of in the brain a linear physical stimulus being set up in the auditory areas, and then later on you turned it into, oh, that's the ba, I want to throw that in the ba, that in the da, and so on. Or did your brain rapidly and really early in processing segregate into different clusters physiologically? And here's what the patients listen to, and this is just a classic. You'll hear this categorical shift. Remember, these stimuli are getting, it's totally linear in terms of the change of the spectral property, but you don't hear 14 sounds, you're going to hear 3. Ba, 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 da, 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 ga, 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 ga. Everybody detect that's categorical perception. You hear it as 1, even though it's linear, you hear it as 1, then you hear it as another, then you hear it as another, and we do it all the time. It's a very powerful property of human cognition, and this is just, I think, one of the beautiful early classic examples. Cut to the chase, when we did direct cortical recording, we had pre-op psychophysics on the patients, of course, for each person's psychophysics. Each one of you probably did your transitions, maybe it could be one step different than the person next to you, so you want to know each person's individual psychophysics. And the bottom line is using the electrophysiology data. This is work by Rieger, who's back in Germany, Eddie Chang, who's now a very highly successful neurosurgeon at UCSF. Basically, what they found by using clustering methods is that the sound, the physiology of the cortex rapidly separated into 3 clusters, supporting categorical perception at a very early level. And in fact, how early? We've got categorical perception in auditory regions by 110 milliseconds. By a 1/10 of a second, your brain is automatically throwing things into buckets. That's amazing. I mean, it's really, and we don't exactly know how it's working. There's some interesting work being done by Shihab Sharma and Ferrets on this, but really beautiful. And in fact, they're interleaved. And it's not in one spot. So these would be all, let's say, these guys here would be ba-da transitions. And these guys here would be, ga-da. But if you notice, it's not like one group's there and one group's there. They're interleaved. Again, the brain is using these complex networks to support behavior. It reminded me a little bit of the social network talk that we heard earlier this afternoon. In some ways, it's physically and probably mathematically very close in terms of how this happens. Now, recording in the operating room is rough because it's just tough. I mean, you don't have a lot of time, and you can't do very sophisticated studies. So we then developed, in parallel, recording in with patients who have chronic electrodes placed on their brain. Now, these are not doing it because they want to make the faculty at UCSF happy to do research. These electrodes are being put on because these are all patients with what is called intractable epilepsy. What does that mean? Intractable epilepsy means that the patient is having multiple seizures per week and it does not respond to any medication. Right? This is a very, very bad thing for your life, for danger, for stigma, for you name it. It's not good. It turns out if we can localize the onset of the electrical short, you can surgically remove it and you can get cure rates varying depending on the patient between 50 to 90 to 95%. So this is a highly effective surgery. And we record, my lab records at UCSF, California Children's Medical Center, Stanford, UC Irvine, Johns Hopkins, Albany Medical Center, and we just started in Oslo, where we have a big grant. So wherever there are patients, there's not thousands and thousands of them, but they're very unique, so we actually have extended collaboration. So the patient comes in, electrodes either with 1 centimeter separation or sometimes even tighter separation are placed. And they're sitting there. And they're sitting in the hospital bed, off medications, waiting to have a seizure. And if they want to participate, which they usually do, they participate in various studies. And there are many different things going on in the executive control world and so on. But I'm going to really focus really pretty narrowly on language. We'd like to get all this wireless because now the patient has to be wired up, and it'd be really nice if we could make this all wireless, then they can move around the room a lot better. So typically, the minimum time in a plant is probably 4 days, and some people, it may take 10 days to get reliable seizure localization. So anyway, I'm going to switch now from the intraoperative data that I showed you, I think is rich, but hard to get, to the electrocorticography. And these are just to give you a feel. Again, we don't have any input into where the electrodes are put. That would not be appropriate. The electrode location is determined by the clinicians who are evaluating the patient. So we pick our paradigms we're going to study based on where we see the electrode coverage, right? So, for instance, if we were interested in the frontal lobe, we probably wouldn't study this patient. But if you're interested in ventral stream object processing, it could be a wonderful patient. So we basically get the day that they're implanted or the day after we get their CT scan and we fuse it with their pre-op MR, we know where the electrodes are. Anyway, so that's where we're at to. That's where we start. So the first thing we did, we said, hey, let's low-hanging fruit. Wernicke's area. Can we physiologically isolate where we think word meaning may reside and give it a temporal code? So this is a very easy study. Patients heard words, babble, laugh, dock. And these words were also decomposed with these STIRF methods into words that kept all the acoustic energy and all the frequency, but scrambled it. There's no way you can make it out. So the idea is that, let's say that was babble, and that was, well, here was the scrambled babble. If I took babble and subtracted its acoustic energy away from babble, what should be left is the meaning part of the sound file. It's a really, really simple logic. We kept the patients on task by saying, every time you hear a proper name, press a button. We just did that so we knew they were fully aware. So here's what they heard.
Babble, laugh, knock, Martha.
Okay, so that's what they heard, and then we collected the data, and then we just showed the results, which are really, I think, quite nice. You're going to see the electrical activity in 4 patients evolving for the word minus its acoustic file, the residual, what we would refer to as the word meaning area, and you can just see it evolve in real time. Okay, here's the word coming on. This is what we've got slowed down, of course. So you can see at 100 milliseconds, we're picking up activity in each patient. So it'll pick up. In the superior temporal sulcus, superior temporal gyrus, these classic posterior Wernicke's area brain regions. Not precisely in the same spot in each person because no one is precisely in the same spot in 3D space, but all in that area. And then if you look at this and look at the actual activation, you see in each patient, the word meaning area is in the superior temporal sulcus and superior temporal gyrus, middle temporal gyrus there, and there. You didn't see in the time file, but it comes on and is finished with extracting meaning by about 200 milliseconds. And it is stochastic. And it is all set up to make errors, right? I mean, it is not like every response is actually perfectly the same. There's a distribution. There's really, truly a stochastic physiological response to different words. So what we liked about this is that there's our friend Wernicke, and basically there's one of the patients, and here's Nina Dropper's cohort of 13 patients with chronic Wernicke's aphasia. That's where the lesion overlaps. You can see it right there. So you put this and this together, and you can see actually the electrophysiology is laid out in a normal brain, except for the epileptic area, but otherwise normal brain, where the word meaning area is, and it maps precisely with the classic neuropsychological literature. And that's why I was really happy to see your work with the aphasia patients, because I think they provide unbelievable insights into organization of language. Again, from a non-linguistic person looking. But I should say with Nina Droppers, I've been the neurological consultant for her speech in the California aphasia program for longer than she would like me to tell you, basically. Now, what about the front part of the brain? Right? So, this is a paradigm that's used very commonly preoperatively to map language areas using fMRI. It's a really simple paradigm. It's a simple verb generation paradigm. You can do it for me. I'm going to give you a noun, and you just quickly say an action verb that's associated with it. Ball, perfect, boom, did it, 1.5 seconds. Is there anybody older here who wants to take a minute? Nobody's volunteering. Your time gets a little slower. I'll wait till I interject, because I think, basically, when you do that in a normal person, you get this beautiful perisylvian language area. This is an inflated brain, and you can see Wernicke's area activation, acoustic area, Broca's area, motor area. The problem with fMRI is you really don't know the timing of anything. It's a wonderful technique in many, many ways, but the simple fact is this. It took 6 seconds for the blood flow to get there. It took 15 milliseconds for the sound file to get through your auditory cortex. I've already shown you you've extracted meaning in 200 milliseconds. So we feel that this electrocorticography approach really complements and extends in the temporal domain, and including the spatial domain, which you get on fMRI. So here's a person basically doing this very simple task, and what you're going to see is this remarkable flow of information, starting in posterior temporal lobe, going up into Broca's area, and then ending up into motor areas, which then drive your mouth. And since you drive your mouth when you say something, you're going to see the auditory area fire again. And you're going to see it in real time. And the code is up here. There's going to be a quarter millisecond before they hear ball, or any one of the words we use. And then it's going to unfold. It's a 2-second movie. But since it's so short, I've extended it to 10 seconds so it doesn't just go whoosh by. Okay, onset, boom, I couldn't even get it. Activation, work being done. Frontal areas involved in selection and providing a motor program. Motor areas activated at a second, boom, stay, and hit the airway. So this particular technique, you can track pretty much, pick your cognitive process, you can track it. You can track it in real time. And a little funny aside, remember when I got this move, it took us a long time to get this published. We had this data in 2006. The reviewers kept telling us, why don't we just do fMRI? The New Jersey, do not do anything rash. No kneecap. Anyway, we finally got it, we finally got it published to Eric's credit and persistence. But I think it really gives you just an incredibly elegant real-time view. And kept looking at this movie when I first got it. I remember the night I got it, I was looking at it, and my wife was in my study, and she says, what were you doing? I said, look at this movie. So she does very good, I think, spouse does when they're trying to break behavior. She goes and gets a glass of wine and just puts it next to your right hand. And you reflexively come drinking and it's all over. Forget about the movie, so the next day it can wait. Okay. So what about Broca's area? Is Broca doing okay? Okay, thanks. Very bad. Okay. What about Broca's area? If you ask a room full of aphasia people, and I have 300 of them, is Broca's area active when you actually speak? Everybody says yes. That's the dominant party line. It's been going on since 1868. Is it true? Well, guess what? The answer is actually not true. What I'm going to show you is when you actually begin to speak, Broca's area shuts off. It's actually not a speech output. It's critical for speech output, obviously, but it is not active when you speak. It's doing pre-speech motor programming and selection, as you've inferred. And you can only see this if you do this electrocorticography. So here's the standard model, this perisylvian serial model, beautiful wet dissection of the arcuate fasciculus, you know, perceive and produce, very serial. I'm going to show you evidence that number one, it becomes parallel very quickly, and that Broca's area is involved in the preparation to speak, but then shuts off. So again, the first cases of Broca, this is the patient, I just said patient, it was a good, nice paraphrase of her. The classic patient tan could only speak, could only speak the word tan. This is actually Tan's brain, and that's, I think, what you want to refer to as an extremely happy neurolinguistics professor, because she's holding Broca's brain, and we're about to suspend it in a magnet and do an MRI scan on it. It had been in alcohol since 1868, and the Anthropological Museum let us take it out of the jar and actually hang it in the scanner. I will say, and I'm not recommending heavy alcohol abuse, but the brain was in alcohol for over 150 years. It looks pretty good. I mean, I've seen worse, believe me. But here's where the stroke is, right here. And they never cut the brain, of course. Here's the stroke. And it turns out it overlaps precisely with our cohort of 30 or 40 chronic Broca's patients. But if you note, the cortex is not the key area. The actual key area of damage, overlap between everybody, is actually the anterior insula and the arcuate fasciculus, a different part of the motor system. And in fact, you'll just have to believe me, if you get a restricted lesion in infarct, it only takes out Broca's area, only takes that much out, the patient gets temporarily mute, and in about 10 days completely recovers. All these things suggested to me and others that maybe Broca's area is not the seat of the actual online articulation. So this work was done by Dean Flicker, and I think it's really beautiful work. The Dean is now a postdoc at NYU, and for any visiting faculty, he's going to come on the job market, and this guy is really, he's really good. Plus he was in the Israeli army, and he was an information officer, so we had a deal. He could buy any equipment he wanted through his entire PhD. His desk looked like the NASA space station. But whenever my computer broke, not anybody else in the lab, he helped me. That was our deal. It was great. So this is a study he just published in PNAS. This just came out. Again, and these are multiple patients where he looked at their auditory responses. These are in naming or reading tasks. Their Broca's area responses and their motor area responses. And to cut to the chase, there's massive activation in auditory areas. I've shown you that, big deal. There's also massive activation in Broca's area within about 1150 milliseconds. But as soon as you begin to speak, Broca's area actually shuts off. The nearby premotor and motor areas come on. And this is true. This is at an average level of maybe 50 or 60 trials in, let's say, one of the patients. This is all the patients, all the trials, stacked. And this just, this is irrefutable. Here is 7 patients in each one of their trials where they're maybe doing a repetition task or some single word reading. They see a visual, they see a word appear. And you can see the superior temporal gyrus activation. Here's when they speak. Broca's area, again, linked actually to the sensory stimulus. There's sensory input fairly rapidly in Broca's area. Broca's area stays on, and as soon as you speak, Broca's area shuts off. I mean, it's irrefutable evidence that it really is not the seat of the online speaking. We believe it's related to selection and phonemic articulatory planning, and if you read the paper, a dean who's really probably the first true neurolinguistic person to come out of my lab has really some nice ideas. Okay, so I showed you that you could use this direct cortical recording to get a kind of precise cartography of the electrophysiology of the human cortex. You could use it to perhaps address, well, you could use it to address classic questions by categorical perception. You could use it to delineate the real-time flow of information in perisylvian language areas engaged in language. And we have several other studies in progress. I'm more interested in why do you speak? What do you decide to select? And I have a couple of postdocs working in that area right now on basically semantic interference effects in ECOG and homogeneous versus heterogeneous stimuli, and how does that work? And we have some evidence that the non-linguistic lateral frontal lobe and medial frontal lobe are actually involved in those control aspects. But we'll save that for another day because we didn't want to really present too much material. This is the slide I showed you before from the dean, who is really fantastic. And I showed you this rich microstructure. This is one patient. You can see this rich microstructure. So since I think we knew we had access to these patients, and all of them in the psych department, I'm also a practicing neurologist, and you kind of always have a kind of clinical desire to do something for patients. And we thought, well, there's a lot of work in motor brain-machine interface. I'm sure this group has probably already seen people present on how you can take signals that you want to move left or right and actually maybe control a wheelchair. And we do some of that work, and the prominent guy on campus probably all knows Jose Carmena. But we said, well, there's a lot of people doing motor BMI. Can we do speech? Could we develop a speech prosthesis so that if you had some horrible neurological problem like ALS, could we possibly implant a grid electrode over your Wernicke's area and decode when you thought of a word or a phrase, like I'm hungry, I love you, some way to get communication, and not just categorical selected between two phrases, because that's relatively, I don't want to say easy, but we wanted to see if we could directly reconstruct the entire acoustic file that we're playing in your head. So this is how we started. We already had this information, and then a really tremendous postdoc, Brian Paisley, basically came on board. He's actually going on the job market too. He'd be great to have any place. I gotta get rid of him, so I gotta. That's your job, right? They come in, they get out. You gotta move through. So no. Anyway, he said, I'd like to try to develop this speech prosthesis, and I said, like any good mentor, I said, that's not going to work. Because we can barely get two signals with motor BMI to go left and right in the wheelchair. When you think about a speech file, there's a lot of difference between, orangutan and baseball or whatever. But, he's smart. We had access. Go for it. So we went for it. And the results, I think, are really extremely exciting. And I'll just show you a little bit of it. This is his first paper. He presented 100 words to about 15 patients who had high-density grids on their auditory areas. He then collected the raw electrocardiogram. What electrocardiogram means it's directly from the brain as opposed to EEG, which is from the scalp. And the problem, you say, why don't I do this with scalp recordings? A scalp EEG is picking up the net neural activity from probably that big a patch. It's just not precise. You don't have enough fine detail to really do the kind of, regression analysis and pattern analysis. You just don't have enough information. In any event, he has the waveforms. He comes up with a reconstruction model. Actually, we've tried a couple. One, and I'll show you the frequency-based one. We also have a amplitude modulation one. And he came up with a reconstruction model, and the model basically took the electrical activity and in a way forced it to produce a spectrogram that matched, let's say, this spectrogram. Baseball. Okay, now, for anybody that does modeling, you can model anything if you have enough parameters. So the real question, if it sees information that has not been used to model, can it actually distinguish? So we kept out about 50 of the words, and then they were not used to make the model, and we presented those words to the model, and the model had to simply say, is it orangutan or is it baseball? It was a binary choice. Random is 50%, and Brian got 91% accuracy, which is was really stunning to me. And I said to Brian, So basically, for those of you who are not completely following this, what do we actually do? I want you to think about a piano. The piano has keys. Each key has a frequency. You can strike them at different patterns, different, a different time code with different frequencies. You can be deaf, but if you know what that code is, and you look at someone playing the piano, they go and tell you what music is being played, right? So that's what we're doing. We're assigning to each electrode in the brain a certain frequency sensitivity at a certain piece of time. Okay, so that's the concept. So what did he achieve? I told you 91% accuracy. What does that mean? It's a number. I said to Brian, and that's a really interesting conversation. People in my lab tend to, I don't like to pay attention to anybody, including me. So I said, make a sound file so people can hear what these reconstructed words sound like. And Brian said, no. I said, okay, here we go. Why? He said, it's not science. I said, do you want to get a job? He said, yes. I said, make a sound file. So finally, after this, like talking to the guy's brilliant, like calling him a 3-year-old. And I shouldn't say he's not a 3-year-old, but it's interesting. So what you're going to hear here is the spoken sound file, Waldo structured dot property, and then you're going to hear the direct reconstruction from electrical activity from the human brain. Now, I want to point out, this is just frequency-based. We're now working on phoneme models, and eventually we'll try to relate some of this to semantic field analysis. This is pure frequency. So let's see what you think.
Waldo?
Heard?
Waldo. Structure. Doubt. Property.
So I think you can probably hear what's going on there, and this is our first pass out of the gate. So we'll see, we have lots of stuff going on. We actually just recently did some single phrase reconstruction. So you hear what they heard and what we reconstructed.
That's my fire escape. That's my fire escape.
Right. So there's stuff in there. We have a long way to go. And of course, this doesn't do anything at all for the patient. We're just analyzing the driving of their cortex, right, and decoding their auditory cortex. What you need for the patient is we have to be able to decode from imagined speech when they say I'm hungry. And that's a big effort in the lab. And I'm not going to show you any of that data. It's significant, but it's not robust enough. And you don't want to make a big deal out of it until we get robust. Because as soon as you put this kind of stuff out, the press picks it up, and patients who have problems think there's a cure, and you don't want to go that way. That's at least our thinking. But I will just tell you, we have a good team, and we're pretty serious about this. So finally, who likes Pink Floyd? Okay, I'll scan it. Okay, all right. So turns out we had a bunch of patients that would let pick songs they wanted to listen to in between recording levels. And then we realized we had a ton of Pink Floyd files, basically. Where is she? Isabel. You're there somewhere, right? Yeah. You worked on this. Thank you. Okay, so this is kind of a really fun project, but it's turning out to be more than fun because I think you're going to see music has prosodic elements. And we feel if we can decode music, then we have a way of including reconstruction models for patients, both the linguistic and the prosodic elements. So luckily, they heard this nice long Pink Floyd song.
All in all it was just a brick in the wall.
And it's about, I don't know, you probably know exactly, 3 minutes and 41
all
seconds.
In all it was
something like that.
just bricks in the wall.
Okay, so basically, here's the team. This is Christian Makuta. He's a postdoc from Switzerland who's a classical pianist, and he has 1 more year to finish his psychiatry residency. He came over here to make his career understanding the neural basis of classical music, and he's going to do it with Pink Floyd. It's a little sad because he does not like Pink Floyd, which I find really great. It's just perfect. And then Brian again leads the team, and then one of our talented undergrads involved intimately in the research. So they had all these patients, and and lots of different patients with left and right hemisphere coverage listening to Pink Floyd, 28 of them. They had 2,100 electrodes, and of these, in terms of reconstruction model, it turns out 140 of them were informative. They helped us reconstruct Pink Floyd. And I'll play the sound file, and you can make a decision on your own. Now, I will point out that this is all the electrodes that really worked. Out of all these electrodes, the next patient we're implanting in Albany, we're implanting, typically we would implant somebody with 64 electrodes covering that whole area. We're putting a grid in this patient over this area alone with 250 electrodes with 3 millimeter spacing. We will have a very rich cortical microstructure to hopefully even get better at our imagined speech attempts. And for those of you who do, imagined speech is tough for lots of reasons, but again, topic of another talk. So here's the informative electrodes, and here is the sound file. We did the first couple minutes of the song to create the model, then use the model to decode the last couple minutes of the song, right? You got it's like a standard holdout when you're doing modeling. So you're going to hear this, just the frequency component of the song, of the last 2 minutes of the song, not the entire song, because I remember we're only doing this initial reconstruction on the spectrogram features. So what you're going to hear here is as good as we could get. This is the spectral feature of the last 2 minutes of Pink Floyd, as heard by the patient. Whistle. Words. Okay. That's what the patient heard. In one patient, there's not enough information to reconstruct. Okay, I already told you that, but we're going to have, we're going for much bigger grids. But with this super grid across all patients allowed us to make a reconstruction of the sound file of the second 2 minutes of Pink Floyd that closely approximates the original. What does closely mean? I think the easiest thing when you do this kind of research, here's what it sounds like played back. So this is Pink Floyd played back from direct cortical recordings. We got a long way to go, but I think, your own brain will tell you that obviously the brain makes behavior, so the information's there, and if you can figure out innovative ways to get at the data, you can combine it with computational approaches and modeling approaches, I think you can really make some serious progress. Our engineering colleagues, of course, when we started this about 3 years ago, they said, what do you need? I said, we needed a 250-channel implantable wireless ECOG grid so that we could put it in the patient safely and we could basically, they have a device. So now it's 3 years later, we're doing good, but they've already got the device. Basically, it's this kind of, we're lagging behind them a little bit, but we'll get there. And this idea of, you'd say, God, that's crazy, a prosthesis of the human brain. Trust me, in the 70s when they said they were going to put in defibrillators, a lot of people said you're going to kill patients if you don't put it in now, it's medical malpractice. In 1980, when people introduced cochlear implants, people said it'll never work. Guess what? It works. And I think if this thing works and it works in patients, it could be quite a boost for many patients with really disabling disorders of the language. So I hope what I've shown you is a little bit of a view into this world of electrocorticography and direct cortical recording and what it can do to address and inform interesting cognitive theories about the neural structure of human language. Thank you. in the exact same place in your auditory area, you'd have a different representation. There's some tonotopy, but the farther away you get from primary auditory, there's less tonotopy. So you still, let's say your informative areas would be overlapping, so they wouldn't be identical.
So in order for it to be a feasible solution in medical device sense, each person would have, the training set for each person would be unique.
The training, well, I think no. The coverage of the electrodes would cover both your areas, so we get the data. The harder thing won't be the training set physiologically. The harder thing is to get patients to reliably imagine speech. That's really the hardest part. I don't think it's the training set, because we think, that was done in 15 or 18 patients, I can't remember, and you could get every one, you could get decoding on. So it's not the decoding, I think. But remember, we're driving a system here, right? They just sit there and drive it. When you imagine, sometimes people imagine the word first, some imagine the sound first. There's also this problem when you're trying, we're driving a system, so we know when to look. But the difference between you imagining on this trial and this trial could be a couple of milliseconds. That means you have to search in the feature space to match. And as soon as you search, you can find all kinds of things that aren't real. Right? You did dynamically time warp. You take your model and you can move it along to try to match or stretch it or shrink it. So there's a lot of potential ways you could delude yourself.